We are going to look at the general nucleophilic ring opening of an epoxide. Now, there is another mechanism I've drawn out previously where this is done with a Grignard reagent or an organolithium reagent. And this is exactly the same mechanism in every way. The only difference here is this is for a general nucleophile. So, again, you would have an epoxide. And I'm hoping you remember how to make epoxides. Go look at a different lesson if you need to do that. And I'm going to make sure that I show some stereochemistry. So I'm going to have wedges and dashes. And we're going to put some groups on these positions. Now, one of them, I'm going to put a hydrogen and a methyl group on, and the other one I'm going to put two methyl groups on. So the carbon there on the left is not a chiral carbon, but the one on the right is. If you had two chiral carbons, you're going to end up with two stereocenters. I just didn't want to draw it that way. So what you're going to be looking for is what's on the arrow. Now, nucleophiles come in a variety of different things. The main thing you are looking for here is that whatever is on this arrow is a nucleophile. In other words, it has a lone pair of electrons that it's going to donate to one of these two carbons in this three-membered ring. These could be of many different varieties. It could be a Grignard reagent or an organolithium reagent, as I've shown previously in a different mechanism slide set. You can also use other things, something like sodium borohydride or lithium aluminum hydride, where hydride is the nucleophile. You could use an alkoxide like methoxide or ethoxide. It really doesn't matter. The point is that you use a nucleophile. Now, in my slides, I believe I've used methoxide, so I want to use something different. I'm going to use a hydride so that you can see this was something different than what you had previous. So the conditions I am going to use are going to be lithium aluminum hydride. Again, this is extremely reactive, so you would find this in something like diethyl ether. You do not want an acidic proton present. And then finally, to work this up, you would add an acid source, but that can't happen until after you've used the lithium aluminum hydride. So the whole point is whatever's on the arrow is a nucleophile. Now, you remember the story I've told you guys many, many times about the mole. The mole is your nucleophile. So in this particular case, that mole is going to be a hydride. As you look at aluminum and hydrogen, hydrogen is the more electronegative of these two elements. So when the aluminum-hydrogen bond breaks, or you can have this to a boron if you're using sodium borohydride, the hydrogen will take the electrons, making it a hydride. Now, as it becomes a hydride, it will be the nucleophile. Now, you have a nucleophile, and you think about these two carbons in the ring. The oxygen is electron withdrawing, so it is withdrawing electrons by induction from those two carbons in the ring. And you need to think about which carbon is a better electron donor. You have a secondary carbon on the right and a tertiary carbon on the left. The more substituted the carbon is, the more electron density it can give. So this nucleophile is much more likely to add to the less sterically hindered side when you do this. You do not have a carbocation here. There is no carbocation. And so you're thinking about where is it easiest for me to sneak in here. They are both donating electron density, and the carbon on the left is able to donate, to some degree, but it's more sterically hindered. So you want to go to the side that is the least sterically hindered. It will add to both positions, but it is more likely for this hydrogen and its electrons to add to this secondary carbon. Now, as that occurs, you're basically doing an SN2 substitution. You cannot have 5 bonds to a carbon. And so this carbon-oxygen bond breaks. Oxygen is the more electronegative of the two elements, so oxygen takes the electrons. This is the product for the major product. it still can occur the other way. This hydride could add to the tertiary carbon, and you could break the carbon-oxygen bond over here. So I'm going to show these two different processes. Now this does always occur in such a way that you do this anti-addition. And that's very important when you start thinking about things like stereochemistry and getting the right stereochemistry incorporated into your products. So again, the major product that you would have at this point. The oxygen and the hydrogen that have added are anti to one another. Now, based on what I've done, there is no chirality, but be aware if these were different groups, these would be where their positions are, and that's why I like to initially start with wedges and dashes, because what is a wedge stays a wedge, and what is a dash stays a dash. So this is what you get for the major. For the minor, in addition to these things in the solution, just in case you're wanting to make sure you can balance everything, we've got this chemical species left over. I don't think there's anything else you need to really worry about at this moment in time. There would also be a lithium to balance the negative charge. Now the reason this occurs is because you are able to make a weaker acid-base pair by doing so. That's the whole point of doing chemistry. You are trying to make something more stable. So this is where you're at this point. So regardless of what nucleophile you are adding, you need to protonate in the next step. So if you're using something like an alkoxide, you would use the solvent as your proton source. But since we used a hydride, we'd have a step 2, and this is where our proton is going to come from. And I'm going to show this just from the major product, but be aware it would also occur from the minor product. So I'm hoping I redraw this correctly. Got this guy. Now you add a proton source. This proton source could be all sorts of different things. The point is it's usually a dilute acid or the solvent. But like we said with lithium aluminum hydride, you can't have a solvent that has an acidic proton present. So choose an appropriate chemical species as your proton source. So I said in step 2 we're adding a hydronium ion. We're adding a dilute acid. So your base is going to come in here, remove the proton, and you will give electrons back. So at the end of the day, you make your alcohol. I just want to point out a few things. This piece right here can be a variety of different chemical species. This is what the nucleophile is that you added. It will always do this backside attack. Okay, so this is from the major product. If it were the minor product, I probably should draw that for you, but here comes the minor product for our purposes. this is what would have been the nucleophile. So you can add either carbon of what was the epoxide, but it's more likely to add to the less sterically hindered carbon. And so again, this one's the major, and this one's minor. And again, you can have a variety of different nucleophiles. This is just showing you how to make an alcohol, and I thought that might be kind of fun. You can convert an epoxide to an alcohol, and you can predict which one's major and which one's minor.